Hi, in this short video we want to cover one more section within Chapter 8, which is dealing with nonlinear models for optimization. So this particular session deals with the notion of separable programming. And it's a very important concept because there's a lot of course, as we've gone from the world of linear programs where everything is proportional to that which are not proportional, and now you're in the world of nonlinear. It turns out there's sometimes you can use sort of easy ways to formulate and solve those as linear programs rather than sort of taking your chances in terms of how it's going to be solved by the solving engine in Solver for nonlinear programs. So let's look at the example presented in the chapter, and I'll just cover the Excel pieces and talk about a few highlights. So again, we've been very familiar with this window or glass model. It's been used in a number of chapters. Last time we introduced the notion of we had some nonlinear marketing costs that resulted in us having nonlinear levels of profitability for each of the different products. So we're going to pull that out for a second and just suppose we don't have the marketing costs, but we do have one other complication, that is that the workers that were going to be working in making these new products have been called away for the next few months. And so we still have the hours, the production capacity hours as far as the plant and machinery goes, but they're going to have to work overtime on the staff. So again, we're going to have to now incorporate this notion of, we can produce a few windows and a few doors without incurring overtime, but if we want to produce any more than that, we'll then have to start incurring overtime. So again, before, we had the constraints of hours used must be less than hours available, and that indeed is still valid, but again, the costs of access to those hours has now changed fairly dramatically. So we're trying to just answer the same old question as always, and that is how many doors and windows should Windor produce, but we're now having to keep an eye in terms of what the costs would be, because it's now changing the economics of how much profitability each unit of doors or each unit of windows creates. We took into consideration the economics in the last video when we were modeling the marketing costs, because again, those became applied in a non-proportional fashion. So again, here's some data. In the far left part here, it just says, so you can produce 3 doors and 3 windows on regular time, and that carries a certain cost associated with it. However, if you want to produce any more doors, like if you could produce, say, 1 more door for a total maximum of 4 for the week, so that extra door, though, that you would produce is going to have to be done on overtime. The windows, of course, same thing. You can produce 3 on regular time, and then you can produce up to 3 more, but again, at a higher cost of the labor. So that's sort of the hourly breakdown in terms of what those maxims are and so forth. However, you look on the right side, and again, now we have considered the profitability for each unit depending on whether it was constructed on regular time or overtime. And as you can see, in both cases, the profit per unit decreases somewhat for doors as you go from regular time to overtime, but you'll notice there's a big drop off in terms of the profit per unit as you go from regular time to overtime for windows. So that's the data that's been added to the formulation, and this is what it looks like. And it's always healthy to do this. Is you choose a product, like in this case on the left, it's the production rate for doors, and on the x-axis is the number of doors you're going to produce, and the y-axis is the weekly profit. And so again, it's a simple matter. The first 3 units that you produce are each going to give a profit of $300 each. So for 3 doors, you would have a total profit of $900. And then when you add when you produce that 1 more door, it is only going to generate a profit of $200. Now, notice that you've got a slope for this first segment of the line, and then you've got a lesser slope for the second segment of this line. That is a decreasing marginal profit, basically. So again, you can imagine if you tried to produce 5 or 6 or 7 doors, now you're paying not only time and a half, but double time. And so that would continue to erode the per unit profit. So that's that whole notion of decreasing marginal profit. And here it is for Windows on the right. And again, remember we said it's a much more steep fall off, whereas the one on the left just kind of barely angles right there as it goes from regular time to overtime. But you notice on the right, it's got a real steep angle. Like it changes considerably as you go from regular time to overtime. That's because that big drop, there's a big excess cost for basically producing producing the windows on overtime. So this notion of separable programming goes like this. Again, for each activity that violates the proportionality assumption, which in this case it's the profit per unit is now violating the proportionality assumption, you separate its profit into parts with a line segment in each part, which we kind of showed you on the previous slide. Then instead of using one decision variable, just like the number of doors, you actually create, in this case, 2 variables. One for how many doors you're going to make on regular time and how many doors you're going to make on overtime. And those are down here at the bottom. There's the DR, which is number of doors on regular time. DO is the number on overtime. Same thing goes for Windows. So now instead of having just 2 variables, one for doors, one for Windows, we have a total of 4 variables, again, depending on the product and whether you're using regular overtime. So the proportionality assumption, though, will hold for these new decision variables because you're now, that DR basically can only take a value from 0 to 3, and the DO can only take a value of 0 or 1. In other words, it's 2 separate lines, 2 separate slopes, and each one has a fixed range in terms of how many are available. And that's what we translate as we go into the model itself. So if I look at the notion of the model, the overtime model now with overtime, this is what it looks like. So again, down here we've now got 4 different decision variables. Again, it's doors or windows, but it's whether they're being produced on regular or overtime. And we correspondingly have 4 profit values depending on each unit that's produced in either regular, overtime, windows, or doors. So you'll notice this profit function is just a sum product of these 4 variables or changing cells times these 4 per unit profit values. Now, other stuff is, I mean, these constraints are the same as they were before in terms of number of hours available at each plant and the same, computations of hour used and so forth. So those constraints are the way they always were with this problem. But over here now we have maximum values on doors and maximum values on windows, both for regular time and for overtime. So this number here, 3, which is, again, that's the maximum number of doors that you can make on regular time. So the constraint will be this number here of this changing cells, which is how many doors you create on regular time, must be less than or equal to this maximum value here. So the yellow cells here, basically element for element, must be less than these light blue cells, element for element. And so let me just do a quick, if we zero this out, and let's then run it. And so we'll bring up Excel here, or I'm sorry, Solver, and we'll show you the model here. Again, you're trying to maximize total profit. Your variable cells, or the changing ones, are these the ones in yellow, all 4 of them. You've got your hours used constraint, which is basically saying the column of E must be less than the column of G, and that's great. And this hours, the next constraint is this one about, again, each of these 4 values of the changing cells must be less than or equal to its corresponding 4 values over here in the light blue. So that's the units produced, which is the variable cells, minus the maximum amounts. But the point is, we can now, we've converted what was sort of a nonlinear, non-proportional problem into a linear program. So now we're back to using the simplex LP to be able to solve that. So we hit solve, it runs through it, and it indeed delivers that solution of 2600. So that's this sort of first, this is again, we have this problem. We've got a non-proportionality situation where now it costs more to do the overtime products than the regular time. But what we did was we converted it into a linear program by introducing more variables and also more constraints is what we did. So kind of straight up easy stuff. Let's get back to a few more things that we want to cover with respect to separable programming. So another way is that sometimes you might have a nonlinear or a smooth relationship. For example, like we did with the marketing costs. Remember those were, it was there were costs, or there were things that were squared as a function of the number of doors and the number of windows. Those were basically smooth curves corresponding to the profitability of each of those products. But sometimes what we'll do is, if we indeed have a smooth function, what we'll do is we'll divide it up. We'll basically sort of simulate it by a series of straight line segments like we've shown here. So again, it might be a true smooth function, which is the profit graph here. But what we're going to do is we're going to approximate it by using a series of line segments. And so, again, Solver can readily solve nonlinear programs that have decreasing marginal returns with the advantage that no approximation is needed. Again, however, separable programming approach has these advantages. Again, it converts it to a linear programming problem, which is easier to solve, and it kind of guarantees optimality for that problem that you solve. But it also it allows you to use Solver's sensitivity report, which is much more reliable when you're solving a linear program than when you are solving, say, a nonlinear programming problem. And again, it doesn't mean you have to be an expert, by the way, in nonlinear curve fitting and all that stuff. But what it says is that you can estimate the profit really by just a few points. So hopefully you sort of know the direction that the curve takes. Like back when we were doing Jones and soda, we know that the higher the price we charge for each bottle of soda, the lower the number of sales that will occur. We kind of know the general direction of that. The higher the price, the lower the volume. But then all you need to do is sort of take a few sample points within there, and then sort of estimate what that curve looks like. So you don't have to be sort of an expert in fifth exponential curves and things like that. Sometimes you can just take the data and look at it and identify points that make sense. So now let's go back to the Windor problem, but now we're going to incorporate sort of the two non-proportionalities. One was overtime costs and the other was the marketing costs. Now, last video when we worked on the marketing costs, we literally put in those functions, these nonlinear functions, and those were reflected ultimately in the profit totals. But now we've got both types. We've got overtime and we've got marketing. So here's again some of the data for it. So now again, we saw this from just the last example we covered right now, which was we've got these maximum weekly productions, which we can do some on regular time, some on overtime. And then we also have this, we've got the gross unit profit, which is before considering the marketing costs. And then over on the far right now, we've got our marketing costs, which again are these nonlinear functions of the number of doors or windows you actually make. So what we can do with that data right here, then we could just simply sort of enumerate for, in this case, doors, one product at a time. So let's do doors. We go, okay, if you don't make any, then there's no profit or no marketing costs or anything like that. But if you make one door for the week, here's your gross profit, $375. Your marketing costs are going to be $25 times the number of doors you produce squared, which is equal to $25. And so if you subtract the marketing costs from the gross profit value, this is what your ultimate profit is for the first door that you decide to make. We do a similar one, and our total profit for 2 doors is $650. Well, the difference between $650 and $350 is over here on the right, which is $300, which means the second door that we make will have an incremental profit of $300. We continue that on, and it's $250, and then it drops to $100. Now, again, a key thing to notice there is that it's decreasing marginal profit. So it's what we call a nice, well-behaved function such that the economics of the problem will drive it towards the correct solution. We do the same thing for windows, and you'll see here, check it out on the right. We did the same thing, only now instead of considering just 1 through 4 doors, we're considering 1 through 6 windows to possibly produce. And you'll notice, check it out, the first one has same calculation, but first one has $633 of profit, the next one's $500, then it drops, then it goes negative. But again, it is what it is, and the reason it's getting so negative is that these marketing costs are starting to get really huge. As you to sell that 4th or 5th window into the market, man, you really got to shell out some money for marketing for that. So let's take a look at this model brought up in Excel. And so this is now we've taken those values that we just showed, the 350, 300, 250, 100. That's now again for the first door, for the second door, third door, and fourth door, which can be made on overtime. And then windows, we do the same thing: first window, second window, third window, fourth window. So now we literally have profit values per unit for each of the first 4 units we might potentially make for each of these products. Now again, but we now have 8 variables, and in other words, this first one here is the first door that's made on regular time, and it is going to incur $25 worth of marketing costs. This is the second door that we make, the third door, and the fourth door. Same thing with the windows, first, second, third, and fourth. So what's nice is you've got a total of 8 possible variables, each of which can only take on at most a value of 1. I mean, it's literally saying unit by unit what's going to be the profitability. So your total profit here is again a sum product between the yellow changing cells and the per unit profitability amounts up here at the top. We've got the same old constraints in terms of the governing on the factory hours. And again, now we have a maximum here in terms of each unit of the door. And again, if you look back here, you'll notice that you hit that minus 300 points on the incremental profit for Windows, and it's bad from there on. So we've set that up. It's clear that once you hit this negative, you would never produce the 4th window, because the reason being is you're better off simply not producing. If someone said, hey, I think we need to produce 4 windows, you'd go, well, actually, if we simply don't produce the 4th one, we're going to be better off. It has literally a negative marginal contribution here. So again, I'll zero these out. And again, keep in mind now that again, this is now a linear programming problem using the separable technique to incorporate the nonlinearities or the non-proportionalities of both the overtime and the marketing. But again, keep in mind that the marketing costs are all baked into our per unit profitability values up here at this top. So if we bring up the solver model, we've got sort of the same kind of a situation. We solve it, and we get the solution to the previous one. So I'm going to have to close that previous one. Hold on just a second. So let me close this one and then go back to this one and try it again. That gets me every time. And hold on, it might have something residual in here. I may need to, let me just zero those out. Oops, escape. And then we will solve it. And it comes up again with our desired solution of 4 doors and 3 windows for a total of $2,500 in total profit. Now, again, we've used the separable technique, in this case on the per unit for profitability. So one more thing that I want to show you here would be the following is, and this explained in the chapter, is that you can in fact say, well, let's just go back to our old way of handling those nonlinear marketing costs, and let me just show you this last model with respect to that. So this model now is using the separable method for the overtime, so we're back to just 4 variables and 4 expressions of per unit gross profit. But then we're adding what we did in the prior video, and that is we've got these marketing costs down here at the bottom. And so our ultimate calculation of profit is our gross profit from sales, which is just simply the sum product of the yellow changing cells times the per unit profits minus the marketing costs. So again, now this is sort of a nice blended model because it's got the separable method for handling the overtime, but we're using straight up nonlinear functions in for our costs for marketing. And so if I zero that out, let's take a look at this model. Now this model, well, I'm going to do something real quick, and that is I'm going to close this one and not save it because I changed that formatting. And I'm going to, now this thing again looks the same. Total profit you're trying to maximize. Yellow cells are what you're trying to, those are your variable changing cells. You've got the constraints on the 3 plant hours, and then you've got the constraints in terms of how many units are produced on regular versus overtime for each of the 2 different products. But check it out, we got to make sure we use that GRG nonlinear because this problem, I mean, I'll show you, if we just try to leave it as simplex and solve it, it's going to say the linearity conditions required by an LP solver are not satisfied. Say okay, so I'm going to go back though and change that to the GRG nonlinear because again our marketing costs are truly nonlinear in this case, these nonlinear functions. And we solve it and sure enough it gives us a solution back. Now the point that I want to make about this model versus the immediately prior one is these are just 2 different ways of handling the marketing costs. In the first way we looked at this problem, like just a minute ago, we calculated the marketing cost effects and reflected those in the per unit gross profits. For this model here, we actually are leaving them in their nonlinear form and then taking out these marketing costs later on. Now, kind of keep in mind that they will give slightly different answers once you get off of the integer values, by the way. So, because again, one is sort of an approximation to that curve, and the other one is actually the functions that define that curve. So with that sort of wraps up our section on separable programming. We will see you in class on Tuesday, but it's actually going to be a virtual class, so we'll see you online. Take care, everybody.